Hello everyone. So, this is the fifth lecture in week 3. So, in the previous lecture we were learning about the steepest descent algorithm or the gradient descent algorithm. So, it is just choosing the descent direction dk to be equal to the negative of the gradient of f at the point x k. Okay. So, that is basically what is the steepest descent or the gradient descent algorithm. Okay. So, I gave you the algorithm in at the end of the last lecture, right. So, we will start with some examples. Okay. So, let us start with our usual example x 1 squared plus x 2 squared, and let x naught be any value, it is just x 1 0 comma x 2 0. Okay. So, we know how to find. So, this is a quadratic function, right. So, why is it a quadratic function? Because I can write this as half x transpose 2 0 0 2 x and plus 0 transpose x plus 0, right. So, you can see that h is actually equal to. So, this is of the form half x transpose h x plus b transpose x plus c, where h is 2 I and b is 0 and this is a 0 vector, that is, c is a 0 scalar. Okay. All right. So, given these values h, b and c, we know how to find alpha k. Okay. But before that we will start with. So, we have x 0, that is okay, and we will first choose dk. Okay. So, or rather d 0. So, by gradient descent algorithm, we have d naught to be so the gradient is 2 x 1 2 x 2, right. So, at x naught it is 2 x 1 0 2 x 2 0, and since we want minus g k, it is 2 x 1 0 minus 2 x 2 0. Okay. So, this is basically the value of d 0. Okay. And we will now find alpha 0. Alpha 0, you can recall, is minus d 0 transpose g 0 by d 0 transpose h d 0. Okay. So, d 0 transpose is just minus of g 0 transpose, right. So, this will be g 0 transpose g 0 by, so h is 2 I. So, I can take that out, 2 into this again is g 0 transpose g 0, right, because d 0 is again minus g 0 and d 0 is again minus g 0. So, you have this. So, alpha naught is actually half. Okay. So, note that for any x naught that I have chosen, I mean I did not choose any value like 5 comma minus 4 or something like what I chose in the previous lectures. So, I just chose any general x 1 0 x 2 0, and it turns out that alpha 0 is actually equal to half. Okay. So, that is a good thing. Fine. Let us find what is x 1. X 1 is actually x 0 plus half into minus 2 x 1 0 minus 2 x 2 0. So, that is, I mean I should write it as x 1 0 minus x 1 0 x 2 0 minus x 2 0, which is 0 0. Okay. So, that is actually wonderful, because we started with an arbitrary initial point and we applied the gradient descent algorithm, right, and in the first step we got 0 comma 0, the right answer, right. So, the minimum of x 1 squared plus x 2 squared is 0 comma 0, right. So, we just applied the algorithm only once, okay, and we got the right answer 0 comma 0, right. So, yeah, that is, I mean, that actually makes, I mean, tells you that the algorithm is really powerful, right, because the algorithm is very simple, because I mean, yeah, you just chose the descent direction to be the negative of the gradient of f at x k, and alpha k, I mean, since it was quadratic function, I just chose the exact line search formula, okay, and in one step I got the answer, right. So, this actually I mean, when you look at this example, it is tempting to think that this will happen for any possible function, is not it? Yeah, that would have been good, because I mean the course would have ended right over there if that were the case, okay. But unfortunately this is not even true for quadratic functions, okay. I will show you an example now where you actually take so many steps, okay, just for a simple quadratic function, okay. So, let us do that. So, let f of x 1 x 2 equals 4 x 1 squared plus 2 x 1 x 2 plus x 2 squared. So, this is again of the form half x transpose h x plus b transpose x plus c, where h is 8222, right. So, this is since we have half, you have 4 x 1 squared, again x 2 squared, and here because of the sum you have 2 x 1 x 2. So, b is 0 0 and c is 0, okay. So, again we so this is a quadratic function, no questions on that, okay. And yeah, let us take some value, okay. You can take x naught as, let us say 4 comma minus 5, okay. I am just taking some arbitrary value, and we will apply this particular algorithm, okay. So, I will do that in Python by Python coding, okay. So, first let us actually implement this algorithm and then see what happens during I mean, so when we implement this particular f with this particular initial point, okay. So, I will start with importing numpy, and we will define f of x to be 4 x 1 squared plus 2 x 1 x 2 plus x 2 squared, and the gradient is, you can compute it easily, 8 into x of 0 plus 2 into, oh okay, so I should have written as 4 into, yeah. So, 8 into x of 0 plus 2 into x of 1, that is the first component, and the second component is 2 into x of 0 plus 2 into x of 1, okay, fine. Now, let us write the code. So, we will start with the initial point, which is yeah, I said 4 comma minus 5, let us stick to that, and h is, as we all know, it is sorry 8 to 2 2, and then we will also define k as 0, k is just the iteration number, and while np dot linalg dot norm of grad of x is greater than 1 e minus 6. So, here I can just write down alpha very clearly, which is grad of x dot. So, maybe I will write yeah. So, please note, I mean, so instead of NP dot of x comma y, I can write it as x dot of y, both are the same. Okay. And here it is grad of x dot of h at grad of x. Okay, I am just writing it in shorter format. So, please note that NP dot of x comma y can be written as x dot of y, both are the same. Okay. All right. So, that is alpha, and x is actually x minus alpha into grad of x. Okay. So, yeah, I could have written it as d equal to minus grad of x and x is equal to x plus alpha into d. So, I just combined both those lines, and k equal to k plus 1. Yeah. So, yeah, one other thing is we need to print the values. So, we will print with some format specifications, so that yeah, I mean, we understand what is going on rather than printing as such. And yeah, so we will also print. So, this is k, and here I want to print x of 0, x of 1, and finally I also want to print the norm. Okay. Okay. All right. So, yeah, please note that for x 1 squared plus x 2 squared, the answer was obtained in one step. So, here I have some 4 x 1 squared plus 2 x 1 x 2 plus x 2 squared. Let us see how many steps it takes. Okay. Oh, there was a spelling mistake. Another problem. Okay. So, let us check now. Oh, yeah. So, there is a percentage that is missing. So, this is not the problem. Yeah. Okay. So, you can see for yourself what has happened, right. So, we started with 4 minus 5, right. So, the next step it came to 1.1 minus 4.737, the next step it came to 1.376 minus 1.72, next step was 0.3789 and minus 1.629, and so on, so on, so on, so on, so on, so on. At the 30th step we got 0 comma 0, right, which is the right answer, right. So, note that when we had x 1 squared plus x 2 squared, we got the answer in one step, but when we twisted f of x a little bit, we made it 4 x 1 squared plus 2 x 1 x 2 plus x 2 squared. The same algorithm has taken 30 steps. Okay. So, what this tells us is this algorithm may not be that good as what we perceived it to be. Okay. So, yeah, we will actually plot this, I mean, to just show you what is happening. Okay. So, in Python we can also do plotting, just that I mean, during the introduction I was not able to cover that. Okay. So, yeah, this is something possibly I needed to have told you at the end of last week, I mean if there are certain things that were missing in the past weeks, we will cover them then and there. Okay. So, at this point I will first teach you how to plot, okay, and then I mean we will plot I mean these 30 points to just see the trajectory of how I mean we started with 4 comma minus 5, let us see what steps it took to reach to 0 comma 0. Okay. So, fine, we will start with plotting. Yeah. So, suppose you want to plot the function e power x. Okay. So, I mean you know that the function looks like this, right. So, let us do it at this point. Okay. First you have to import a library called matplotlib.pyplot. Okay. So, yeah, since I do not want to write it this big every time, I will write it as PLT, okay, like we import numpy and then write it as NP, right. So, in a similar way we will import matplotlib.pyplot and then write it as PLT. Okay. So, if you want to plot e power minus x, we should have a range of values, right. So, what are that range of values? So, let us pick values from minus 5 to 5 in steps of 0.1. Okay. So, let me define x as the array of values which contains values starting from minus 0.5 to minus 5 to 5 in steps of 0.1. Okay. Yeah, we'll start from minus 5 and then go until 5. Okay. So, for this I define this following function. This is also something I did not teach you. Okay. Okay. So, what does this do? It actually initializes x as the following vector. So, the vector is the following minus 5 minus 4.9 minus 4.8 dot comma 4.8 4.9 and 5. So, the last value is not taken into account. Okay. So, if you write 5, it will stop with 4.9, that is basically what I want to say. Okay. So, yeah, so this is just to I mean this just creates an array of AP, okay, that is arithmetic progression. Okay. And the command is numpy dot a range. So, do not read it as arrange, okay, arrange has double R. So, this is a range. Okay. Fine. Oh, I am sorry. Okay. So, that is x, y is np dot exp of x, okay, that is just e power x, right. Yeah. So, I have given what should be there in the x axis. X axis should have values from minus 5 to 5 in steps of 0.1, and in the y axis you are going to have e power x, right. So, let us plot it now. So, the command is plt dot plot of x comma y, and you also have to finally write plt dot show in parenthesis. Okay. So, only then you will see the plot, otherwise you will not see the plot, please understand. Okay. Fine. Yeah. So, here is the plot, you can see that it starts from minus 5 below and ends at plus 5, and you have a nice e power x curve, right. So, we can plot any other plots of this sort. Okay. So, for example, I mean those who have some knowledge on machine learning would be aware of sigmoid function, right. Sigmoid function is 1 by 1 plus e power minus x, right. So, let us plot that for values from minus 5 to 5. Okay. So, that is very simple, you just write 1 by 1 plus e power minus x yeah. here you have the sigmoid function, where so at 0 you can see that this is equal to half, right. So, yeah, so that is all is the plot. So, you define the x axis, define the y axis, and you just get the plot, okay, fine. Now, suppose I want to plot these points, okay. So, I want to start with 4 comma minus 5, that is one point. The next point is 1.102 comma minus 4.737, so that is the next point. The next point is 1.376 comma minus 1.72, and the final point is, yeah, where you reach 0 comma 0, okay. So, how do you plot this? So, you could have, you should have realized that in the x axis you should have all of these values, and in the y axis you should have all of these values, right. So, I will write them as y1 and y2, since we are using x for something else, right. So, I will start with y1 as x of 0 and y2 as x of 1, okay. And at each point I will append x y1 append y1 comma x of 0 and y2 is okay. And since we have the vector of y1 and y2, we can now plot, we first plot and then show. Yeah. So, you have these 30 I mean the 30 iterations, whatever has happened, you are seeing it here. And what is happening here? So, it started with minus 4 comma 5, it moved here at this point, then moved here, then moved here, 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 and you finally reach 0 comma 0, right. So, the best way is actually to reach through a straight line from 4 comma minus 5, you go straight like this, right. That is the best thing to do, is not it. But what has happened in this algorithm is it is going zigzag, starts from here, this way, 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 right. So, I mean to make it precise of what is actually happening, you would have liked it to travel like this as a straight line, right, this way, but it goes like this, is not it. So, and note that this happens like this for the, I mean when your function is 4x1 squared plus 2x1 x2 plus x2 squared, yeah. So, when it is this 4x1 squared plus 2x1 x2 plus x2 squared, but when it was x1 squared plus x2 squared, no issues, it was just in one step, it was a very nice trajectory. So, if you want me to do the, if you want me to plot that as well, that is very easy. I mean I just, so I have everything ready, I just change f of x, grad of x and h, okay, and I get yeah, the answer for x1 squared plus x2 squared, right. So, let us just do that, x1 squared plus x2 squared, and here you have 2 into x naught comma 2 into x1, and here it is just 2002, okay. So, you can see that it starts with 4 comma minus 5 and ends at 0 comma 0, a straight line. Why is this the case? So, it works so well for x1 squared plus x2 squared, but it has kind of failed miserably for 4x1 squared plus 2x1 x2 plus x2 squared. So, you can actually see that I have not even made it 3 dimensional or 4 dimensional or anything, it is still 2 dimensional and it is still quadratic, it is not even cubic or exponential or logarithmic or anything of that sort, the function is still quadratic. From x1 squared plus x2 squared I just moved to 4x1 squared plus 2x1 x2 plus x2 squared, but the performance has gone berserk, right. So, why is this the case? Okay. So, I will give you a gist of what is, I mean, or rather why is it going wrong, okay. And then we will actually I mean analyze it mathematically in the next class, okay. So, the gradient descent or the steepest descent algorithm performs very well if a quantity called as condition number is close to 1, okay, 1 or close to 1. The moment it gets far away from 1, okay, the performance deteriorates, okay. So, when I say this you should actually ask me what is a condition number, okay, I will define it. So, the condition number of a matrix, okay, of any matrix. So, let us consider H is equal to lambda 1 by lambda n, where lambda 1 is the smallest eigenvalue of H and lambda n is the largest eigenvalue of H. Okay. So, and I will write down the statement that I just made now. When lambda 1 by lambda n is close to 1, gradient descent converges to x star fast, okay. When lambda 1 by lambda n is much less than 1, gradient descent converges very slowly. Of course, it converges, that is not a problem, okay, but it could take many steps, okay. So, what is the condition number when your f is x1 squared plus x2 squared? So, H you can see that it is 2002. So, the eigenvalues are 2 and 2. So, the smallest as well as the largest are equal, okay. So, lambda 1 by lambda n is equal to 1, leave about approximate, it is exactly equal to 1, right. So, thus the convergence was just in one step, okay. Instead, if you write lambda 1 by lambda n is very less than 1, okay. So, here it is not very less than 1. So, let us see what is the case for this H. So, you can see that the sum is 10 and the sum of eigenvalues is 10 and the product is 12, right. So, yeah, it is roughly something like 8.5 1.5 I think, yeah. So, when you write 8.5 and 1.5 you will get 12.75. So, yeah, roughly around that. So, if you divide 8.5 and 1.5, so you get about 5.6 or something of that sort, right. So, that is why you saw that it took 30 steps, right, to converge to the answer. So, yeah, you can just see this from the condition number. In the next class I will discuss why condition number is so important for the faster convergence of the gradient descent algorithm. Thank you.